Hello, my name is George Porter from UC San Diego, and with my colleagues Max Millett from InFocus Networks, Alex Vrencic, Rukshani Athapathu, Alex Noren, and George Papin, I'd like to present Realizing RotorNet towards Practical Microsecond Scale Optical Networking. I'd like to start by talking about three large trends in data center networking, and one of them has to do with higher bandwidth endpoints. We're seeing the deployment of accelerators like GPUs and TPUs that have been driving very large amounts of bandwidth inside of boxes and in between boxes. That's a challenge for network operators to keep up with. We've seen increased heterogeneity as different parts of our network are upgraded and replaced with newer components. There's this question of how to interconnect those devices. Do we need to upgrade the core of our network to match the fastest devices in our network, or can we do something in between, or something else? And finally, we're seeing increased workload specialization with topologies tailored to large workloads like AI and ML training, for example, torus-based networks, where different jobs may be optimized based on different sizes and structures of those particular networks. And so how do you design a network that's flexible enough to support different workloads and applications, even as those applications suffer from things like failures in tightly coupled computations? So these three trends, among others, have led to a motivation for introducing optical circuit switching into data center interconnects. So it's just a brief summary of what optical circuit switching and optical networking is. Here's an example taken from the Liu et al. Paper in SIGCOMM'23, where we see a technology-dependent switching element that forwards light from an input port to an output port. We can't read packet contents because the light is just flowing through the device uninterpreted, and so they're externally controlled. And that input to output matching or mapping changes slower in general than a single packet transmit time. This reconfiguration time is a very important parameter for our system, and it means that we're in the regime of circuit switching, not necessarily packet switching. On the other hand, though, we don't need transceivers, which saves energy and cost. And these devices are bandwidth agnostic, unlike packet switches. And so they don't have to be upgraded or replaced when we upgrade or replace parts of our data center network. We've seen this technology deployed in practice. And so Google has some papers. This is taken from last year's SIGCOMM, showing optical switches deployed in practice. In the middle, you see this Palomar optical switch, and on the right, what you see is a core element of that switch called a MEMS mirror array. So this MEMS OCS device has a reconfiguration time, input to output port matching change, in milliseconds, leading to really an end-to-end systems level reconfiguration in seconds, minutes, or longer time scales. So we're going to call this slow switching. The question is, can we move from slow to fast switching, and what benefits might we get? So this MEMS switching is great for changing the topology between jobs or in responding to failures. But what if we could adjust the topology within a job's runtime as the communication behavior changes in different phases of the application, or potentially to directly connect high-speed accelerators, for example, to storage, when those applications need that? This has the potential to increase efficiency, lower cost, and lower energy. And as a result, it's attracted a lot of interest from the research community. And if you look in our paper, you'll see references to projects that have focused on fast switching, and there are also others as well. So we're interested in this paper in how to do practical fast data center optical switching. So in SIGCOMM 2017 and NSDI 20, we presented the design for a system called RotorNet, which was an initial design focused on an oblivious control plane, support for low latency packet transmission via a multipath and expander graph method described in that paper. But that prototype was built with really the same type of slow OCS that you see in these deployed networks like the Palomar switch. So what this paper is about implementing and validating a low latency bespoke protocol called Opera with a device that we engineered, which is a non-MEMS rotor OCS switch device. This is a novel device we built for this project, and it was designed from the ground up to work with commodity optics and data center environments. And so this talk is about our experiences building this network and the lessons that we learned in that process. Now you might ask, can we build a faster switch by just making the OCS go faster. We'll just, whatever, put more energy into it or turn the knob to make it go faster. And the problem here is that current OCS MEMS designs can't easily be made faster while keeping port counts, switch radixes that are relevant for today's data centers. So if we take that Palomar switch we showed earlier, you look at that MEMS array, what you see is that a mirror has to physically move in space. This is an analog device in order to steer traffic from an input port to an output port. Now, if we make a very small number of ports, we can have small and fast mirrors, driving that speed up at the cost of a small radix. But if we keep the larger radix, we end up with these larger and slower mirrors. And so we end up with this tension. So faster crossbar MEMS leads to fewer ports, which undercuts the benefits of optical switching. Now, there are alternative research technologies that are either low port count or rely on non-commodity optics that are of interest or interesting. But since optics are nearly half the cost of the data center network, ballpark figures, we wanted to kind of focus on something that would work with commodity optics. And so we were faced with this device level limitation using this particular type of switch technology. And to give you an analogy in a little bit of a different domain, imagine storage. So imagine you have a system with storage level storage requirements here on the top left of the screen, and the device that you have is not capable of implementing those requirements. We have much smaller capacity, bandwidth, fewer IOPS, higher failure rate, etc. Now you can imagine kind of working on different ways of making this device better. We could add more spindles, we could put more disk arms in there, etc. But what you end up wanting to build actually is something like a RAID storage array solution. So rather than making the device meet the requirements, we are going to take a device that does not actually meet the requirements, put many together, and build something at a systems level that gives us what we want. We can spread data across the devices, use replication encoding theory to mask failures, distributed replication to mask geographic failures, etc. And so the key insight that comes out of this is that the system can realize attributes that are hard or impossible to implement at the device level. And that's exactly what we're going to do as part of this device that we're building. So instead of building a crossbar network out of crossbar switches, we're building a crossbar network out of non-crossbar switches. So what do we mean by that? Well, a crossbar network allows you to connect arbitrary input ports to output ports based on whatever the requirements of your network are. And so this means that these switches have to implement essentially a factorial number of matchings, and we're selecting and searching between these matchings to find out what's best for the network at that instant in time. Instead, what we're building is a non-crossbar switch model where an individual device is only going to have a very small number of matchings that are not factorial number. And instead, we're simply going to cycle through these over and over and over again, and we'll be able to send traffic potentially through the switch multiple times to get it to the destination that we'd like to get it to. So zooming out a little bit, if we have a strawman sort of crossbar network, even for modest n equals 16 hosts, the crossbar is going to have to implement n factorial matchings, no particular fixed sequence. On the other hand, this RotorNet network we built, we can do with only 16 matchings, which is much smaller than 16 factorial. And in fact, we're going to spread those matchings across, in this case, 4 rotor switches in the middle of the network, so that each rotor switch is only going to have to cycle through 4 matchings. And so there's a very small number, which means we can make it fast, we can make it very high port count. And as you can see kind of on the right, end devices can select rotors, potentially multiple ones, to forward traffic from the source to the destination using whatever matchings get it to the destination. Okay. On the left is a picture of our current rotor switch design. What you see is a fiber bundle that comes into the switch. We're using lenses and mirrors and microprism array, reflectors in order to focus the light from those fibers onto a spinning disk. And this disk has gratings along the edge that implement the different matchings. And because it's a circle, it's implementing them in a cyclic manner. And on the right, you see the switch deployed at the UCSD data center in a 3U enclosure that's packaged for the environments that you would see in a chilled data center, for example. Now, Here's a couple things that we did in order to focus on practicality, and in particular, the ability to manufacture these devices at the budgets that we had at a university. So we had to focus a little bit on low-cost manufacturing. So the first thing that we did was we implemented our rotor using a hard drive spindle. So we took a hard drive apart, patterned it with gold, and then we laser etched these diffractive dissectors around the edge, which implements all the different matchings that we needed for our topology. Now, this laser etching process is inexpensive, so we were able to implement it on a university budget, but it leads to small point defects on the surface. This is similar to when you have an audio CD that is skipping. And so one of the big questions that we had was, what is this going to do to the throughput of TCP and commodity optics when we encounter these point defects due to this low-cost manufacturing mechanism? Another thing we did focused on practicality was, rather than having to manufacture 4 different rotor discs, which would be quite expensive, what we did was we created 4 identical discs, or n identical discs in general, and we can simply permute the way we connect the fibers to it to implement whatever matchings we'd like, and in this case, the ones that we decided we need for this particular deployment. What this lets you do is stamp out these discs in batches, again, sort of similar to how audio CDs are made, very low cost. We're interested in supporting standard end host protocols, for example, TCP, Linux, etc. And so what we see along the top here are the components that are part of our system. So on the left, we have the host. Then we have an FPGA NIC based on the Corundum platform developed here at UCSD, and our rotor switches on the right. In order to interface to the rotor switch, our NIC has to keep a set of forwarding rules that it updates every time this disk goes to the next sector. This is actually, so that synchronization is done with the precision time protocol. And what's nice is that this means we don't have to control the transmission of individual packets. We just have to change the set of forwarding rules at sort of tens of microsecond timescales, which Linux can handle, and which, excuse me, our Corundum NIC can handle quite well. And so a big question we had was, okay, well, given the composed system, what's that going to do to things like ping times and application level latencies going through that switch? So in order to evaluate this, these 2 questions on the left, we took a 16 server testbed, 2 devices, 2 NICs within each server, so that's 32 emulated devices, and we connected that to a 128 port bidirectional rotor switch divided into 4 subswitches. And again, to save in terms of manufacturing costs, we actually etched 4 different rotor switch tracks into our disk, so literal tracks in the disks, in order to implement this with a single rotor. When we deployed this using commodity TCP, we were just under 10% away from our link rate. And when we looked into why that was, what we saw was a lot of retransmissions due to those point defects. Now, rather than choosing an alternative, much more expensive manufacturing technology that would lack those defects, what we did instead was something quite simple, which was we empirically measured and scanned the disk to find the defects. We remembered the locations where those defects were. They're going to come up every time because that disk is just spinning round and round. And so what we end up doing is we just delay packet transmissions during those brief periods where we have these point defects. And what we found was that in doing that, we cut the number of retransmissions, which drove up our relative link throughput to very close to link rate. So within very close to the ideal link rate. So that was very promising. Now, what about latency? On the left, you see a graph, and on the right, you see a graph. So the left shows the round trip latency kernel to kernel for ping, and the right shows round trip latency user space to user space, similar to, for example, an RPC framework. And what we see are the comparison of our low latency opera protocol through our rotor switch, both at a loaded and unloaded background traffic, as well as a comparison to a ConnectX-5 baseline, both directly connected to servers back to back and connected through a switch. And what you see in terms of our results are comparable minimum and median latencies with that ConnectX-5 platform, slightly worse 90th percentile latency due to the fact that our packets sometimes transit the switch multiple times, but slightly better latency above the 99th percentile. And we attribute that likely to small differences in batching behavior corundum versus the ConnectX-5 NIC. So in summary, we've demonstrated a practical path to implement a rotor-like optical network at scale, designing, manufacturing, deploying, and operating a 128-port bidirectional optical rotor switch, developing NIC hardware and host software to make that happen, and working with commodity optics, which we think is really important because that's a key driver of overall data center network costs. We have the first real-world measurements of Linux TCP throughput and host-to-host latency through an actual RotorNet, and we show near link rate bandwidth with 99th percentile ping times faster than a commodity packet switch hardware. And what we've really validated is this choice of a unique switching element and the co-design of hardware and the protocol in order to simplify the design of the rest of the system and to lower the cost of manufacturing. So with that, I'd like to thank you for your time and thank you for your attention.